Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to Optimization in Civil Engineering. In the last lecture, you looked into the optimization methods for the multivariable optimization problem. In those methods, we used various techniques, but we also understood that those techniques were not very efficient and particularly were not very intelligent to converge into a optimum solution. It actually indicates that there is a need for methods which can actually use the pattern or the objective function values trained and reach the optimum solution or reach closer to the optimum solution faster. So in today's lecture, we are going to discuss a few such methods and we'll start with that. The primary direct search methods are random search method, grid search method, univariate method, and pattern search method. There are two other methods which exactly does not fall under these four categories are evolutionary optimization method and simplex search method. Now in the last class we discussed about the random search method, grid search method and univariate methods, and we said that before we discuss the pattern search method, we should be discussing two other methods which can help us to understand the need of the pattern search method better. So for that reason, we are going to discuss the evolutionary optimization method and simplex search method in today's lecture. So let's start with the evolutionary optimization method. The evolutionary optimization method uses the n-dimensional hypercube to search for an optimum solution. This n represents the number of variables in the objective function. An objective function with n variables is evaluated at the 2 to the power n corner points and at the center of the hypercube and then compared to obtain the best possible solution. This best possible solution at the location is further used to develop another hypercube and review the objective function at the corner points as well as at the center point. This process continues until we reach to a point that no further solution can be obtained at any of the corner points of the hypercube and the cube size is shrinked to the level of precision we have pre-decided. So in case of two variables, we can say we are looking into the four corner points. So two variable, if we are representing, we can say that two corner points for one variable and variation, and the other two corner points are for the variation of the other variable. So these are the four corner points in case of two variable and as well as the center. So in this method we do evaluate the objective function value at the four corner location and at the center. Once we compare the objective function value at all these location and choose the location where we have the better solution. For example, if the better solution is here, then we use this as the base point and find the solution or develop the cube around that by setting up the location like this, and the process continues. So in case of cube, you can imagine we are dealing with 8 corner locations and as well as the center. So if the number of variable increases, it is going to increase in that order. So now let us look into the algorithm. In this algorithm, we need to start from a point which has to be given, or we need to randomly choose that point. Then this point is going to represent a vector of n variables. Then we need to also decide on the hypercube edge size at the beginning for each variable. Now this edge size could be different for different variable, or we can have the same size for all variable. The size depends on the sensitivity of a particular variable. If a variable is very sensitive, then in that case the size should be small. If the variable is not very sensitive, then we can have a larger size for that. We also need to decide on the sufficiently small precision level, which can be used to decide when to stop or terminate the process. So once we have all this information, we move to the step 2, where we first check the step whether it is within the precision or more than the precision. If it is more than the precision level we have set, then we create a hypercube with 2 to the power n points, or 2 to the power n corners, which surrounds the base point which we have started or selected. And this is done by adding or subtracting the half of the edge size from the x point. Once we do that, we compute the objective function values at those corner points and compare them to find out the best possible point. By any chance, if we find that the edge size is less than the precision which we have set, then we are going to terminate the process and report the x value as the optimum solution. So once we have developed the hypercube and evaluated the objective function at the 4 corners as well as at the center and found the best possible solution, then we move to the step 3. In this case, we use the best solution of step 2 and see whether if it is equal to the objective value of the base point which we used to start, or the point obtained in the previous iteration. If we find that these 2 points are exactly same, then we need to reduce the step size. So we are reducing the step size by half, and then again go to step 2 to form another hypercube. Or before we form the hypercube, we check whether we have reached to a sufficiently smaller edge size, and if we haven't, we develop the hypercube and obtain the solution. If we find that the new point is different from the earlier point, then we need to set the optimum solution of step 2 as the new x, and then we need to go to step 2 with the same step size, and this process will continue until we reach the precision level. So this method is going to be easy to understand through this example, and in this example we are using the objective function which we had used earlier as well, and in this case we are starting at a point 5. There are 2 variables and we are setting the precision as 0.3 and the start edge size is 2. So we are looking into a cube, or in this case 2 dimension means a square of size 2 by 2. So this is also 2, this is going to be 2. Now with this, let us look into the solution. So the first point, as we said, which is a 5 and 5, and at this point the objective function value is 400. Then around 5 and 5, if we look into the 4 points, if we look into 5, 5 and subtract half of the step size, then it is going to be 4, 4. This is going to be 6, 4. Then this is going to be 6, 6, and this is going to be 4, 6. So for this as a center point, once we find out all the 4 corner points, then we evaluate the objective function value at all the 4 corner points and then compare. And if we compare, we can clearly see that the objective function value at this location is better than all the other locations. So this location is better. So using this as the new center point, which we can see here, we develop the 4 corner points based on the same principle and then find out the objective function value and compare the objective function value to obtain the best one. And here is that. So this point becomes my new center, which you can see it here. And this process continues until we reach the point 0, 0, and once we reach there, the objective function value becomes 0, 0. At this point, this is the best location, so we consider this as the center location in the next step, and then we find other points. This is -1, -1, 1, -1, 1, 1, and -1 and 1. And all these 4 corners, we see that the objective function values are higher than the objective function value at the center. So at this stage, we need to reduce the step size. So in this case, from 2, we reduce it by half to 1. And then again looked into the 4 corners. Now the 4 corners are shown here. And if we evaluate the objective function values and compare with the objective function value at the center, we still find that the objective function value at the center is better than all other 4 points. So we further reduce the step size, make it to 0.5, and again check, and the same thing repeated. So we do reduce it to further 0.25 and check, and found this to be the optimum point. And at this stage, we see that the step size is less than the precision which we had set, and hence we are stopping the method here and reporting 0, 0 as the optimum location with objective function value as 0. Let us look into this solution in a graphical format. So we started at a point 5, 5, which is the center point, and the 4 points are here. And when we evaluated the objective function value at this 4 point and compared with the objective function value at the center, we found out that this location objective function value is the best among all the 5. So we use this as the new center point and then develop the hypercube, in this case a square, which has the corner here, 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 and this is already there. So once we evaluate the objective function value this level and compare, we find that at this corner the objective function value is less. So using this, we developed a square grid, which is here, and once we compare again, we find that this is the better one. We again continue. As we move, then we reach to the point 0, 0 here, and the 4 corner points are at this 4 location. If we compare, we still find that the objective function value at this center is better, so we reduced the step size and found the 4 corner points after reduction of the step size. And once we do that, then again we find out that the center point is better, so again we reduce the step size, and gradually in the few iterations down the line we find the step size is sufficiently small and lesser than the precision value which we have set. Now in this whole process we can clearly see that we started from this point and we are moving in certain direction looking into the objective function values. However, the method did not explore this pattern, it just went through the lowest point and went to the optimum point. So it actually indicates if we can make the method little bit intelligent, then we can actually reach the optimum solution faster. The other concern with this particular method is that in every iteration we are required to evaluate 4 objective functions. And as I said earlier, if the objective function value evaluation is quite complex, then it is going to take up a lot of computation process. So if we can exploit this pattern, then we may have a better chance and may require less number of function value evaluation. Now you can imagine if you have more than 5 or 10 variables. So if you have about 10 variables, you require to evaluate 2 to the power 10 number of objective function at each iteration. This is quite a large number. There is another method which can actually use less number of objective function evaluation and use the pattern to some extent to reach to the optimum solution, and this method is known as simplex search method. So a simplex is the generalization of a triangle or tetrahedron to arbitrary dimension. Now in this case the objective function with n variable are required to be evaluated at the n plus 1 vertex. So it is quite less than the number which we were looking into in the previous method where it was 2 to the power n. Now the objective function value at each vertex are compared, and the vertex with the worst objective function value is reflected away towards the better location, and this is where we look into the pattern to some extent and extend our search in that particular method. So overall this method requires lesser number of function evaluation compared to the evolutionary method, and while developing the initial simplex, one has to be very careful in this particular method because we are talking about the simplex, and if by chance if all the points are in the same line, then we cannot form the simplex, it becomes a straight line. While we are generating the simplex, we have to ensure that it should not end up developing a zero volume n dimensional hypercube. We'll look into one of the process how to start or develop the simplex for the algorithm. But before that, let us look into the basic concept for two design variable. So for the two design variable, we are looking into 3 vertex. So we have 3 points. These are the 3 points for the two design variable, and then once we look into this 3 point, then we find out the center of that point, and whichever is the worst point among the three, we choose that point to reflect in the direction of the center and beyond. So in this case, if we find this is the worst point among the 3 points, then we use this point to reflect towards the center and beyond, and this reflection or reflected point is here. So we can consider this as the reflected point of the worst point. If we say xw as the worst point, so it is reflected. Now we look into the or evaluate the objective function value at this reflected point. By chance, if we find that this objective function value is better than the best objective function value of the 2 points, for example, if best point is this, so if we represent it by xb, and this point objective function value happen to be better than the objective function value at this point, then we do expand this particular point further in the similar direction. So it is expanded to certain extent and we get this point here. So we can call it the expanded point. So what happens if this objective function value is not at all bad, not at all good or better than the worst objective value we have obtained at this location? In that case, it is not a good idea to go further in this direction. Rather, we would like to contract, and when we like to contract, we have to compare the values. Now, when we are comparing the values and find out that this particular location, the objective function value is even worse than the worst value which we have for the original simplex. In that case, it needs to contract and go inside the original simplex and reach a point like this, very close to the center or beyond the center. Now, it may so happen this value is better than the worst point, but not better than the next worst point. So if this is my next worst point, so I will call it xw1, and we find out that this value is better than the worst point but not better than this, then we do contract, but we do not need to enter within the simplex. Rather, we do contract and still stay outside the simplex and choose a point somewhere here. So this is also a contracted point, but in case this point is representing when it is better than the worst point. And then with this point we get a new simplex of this, and which is used for the further evaluation. In this case, the new simplex remains like this and it is used for the further evaluation. In this case, the new simplex is this and it is used for the further evaluation. There is another chance that we find out this new point is better than the worst point and thus next to worst point, but not as good as the best point we already have. So in that case, what we do is that we keep it as this point for the next iteration, and hence we use this as the new simplex and go for the next iteration. Let's look into the algorithm in details. Before we look into the algorithm, we need to understand the simplex formation, how we can develop the simplex without generating a zero volume n-dimensional hypercube. For that reason, we have an algorithm, and in this algorithm, the first step is we have to choose a start point x0, which represents a vector of all the variables as shown here, and a scale factor SF. Now with the help of this, we are going to generate the other points or other vertex by using this formula. So these other vertex are represented as xj, and when we calculate the location of this other vertex with the help of the variables, we can simply represent the new variable, which is this one, is going to be the variable of the which is going to be the value of the variable of the start point, which is here, and added to that is the scale factor, which is SF, and or the scale factor multiplied with sufficiently small delta. We use the scale factor directly when we find that the variable is the one which is the primary vertex. We add the scale factor when our variable number and the vertex number matches. In all other cases, we actually multiply the scale factor with a delta value, and this delta value is obtained as if it is the number of variables are equal to 3, we consider it as 0.25. In all other cases, we use this formula to calculate the delta value and then use it. So in this method, we are going to generate total n plus 1 points. So this is going to give us n point, and we already have 1 point as this. So total n plus 1 point. With this n plus 1 point, we are going to look into the detailed algorithm.